Thank you for downloading this podcast from The Reedy Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za. The Naked Scientist on Talk Radio 702 and 567 Cape Talk with Reedy Clubby.
Chris, good morning.
Good morning.
Thank you very much for joining us. For a moment there, I was getting nervous thinking technology is going to fail us. Let's talk about plants and mathematics.
This is interesting because the people who have done this piece of research are just up the road from where I am, actually. It's Alison Smith and Martin Howard, who are two researchers at the John Innes Centre in Norwich, Norfolk. And what they have discovered is that plants must be very, very good at mathematics, because when the sun goes down, the process of photosynthesis, which is how plants capture energy from the sun and use it to produce chemical energy in the form of sugars, this process stops. So the plant then has to start relying on stored energy in the form of starch, which it has made from the sugars it made when the sun was shining. And the idea here is that the plant wants to grow as fast as it can, because plants do most of their growing at night, and that means it needs to use as much energy as fast as it possibly can, but not run out of energy. So the plant has to budget, it has to know how much starch is in its cells, and therefore know how much energy to burn over the night, so that when the sun comes up the next day, it has just run out. If it gets it wrong, then the plant will starve because it will eat all its energy up too quickly. Mm-hmm. If it doesn't burn the energy up quickly enough, then it won't grow as much as it could have done, because it could have burned off more energy and put that energy into getting bigger. How does it do it? Well, plants, it turns out, and this paper was published in the journal eLife just last week, plants have a clock. We knew that. They keep time, so they know when the sun comes up and they know when the sun goes down. And they link this clock to the amount of energy they're burning in their cells. Effectively, they do a division. They say, well, I know how much energy is in the cell. I know how much time I've got left in the nighttime before the sun comes up. And therefore, I can divide one into the other, and that tells me how much energy I have to burn per hour. And the experiments show that the plants are clearly doing this. They don't know exactly how yet. They think that there must be some kind of computation being done chemically, obviously, where the plants are using one thing to work out how much is present of the other, and one thing controls the other. But it's still extremely interesting, and it has important applications and implications, because in order to make plants more efficient, to feed more hungry mouths as the world population continues to grow, we're going to need to know exactly how plants do what they do and how to optimize their growing conditions, or optimize plants genetically to make them grow at their best. And so understanding how this works, apart from being academically very interesting, could have an important human impact too.
I was so fascinated by that. Let's go straight to the lines. Leon in Pretoria, hi.
Good morning, Naked Scientist. I just got a question regarding the communication explosion, which certainly makes everyone more informed, or makes them more informed. However, my question is, does it contribute to the increase in the average IQ of the world population?
Hi, Leon. A very interesting question. And you should put your question to Professor Flynn from Otago University in New Zealand, because he has had a thing called the Flynn effect named after him, which is that if you compare the IQ of the average person now with, say, 30 years ago, then based on the tests we're using, a person 30 years ago would have judged to have been an imbecile compared with today. Because the thing is that you can take a person who has lived all their life in the bush and they've never seen writing, they've never learned to read, and if you gave them an intelligence test, they would score 0. That's not because they're stupid. If they can survive in a very harsh environment, they're clearly pretty intelligent, but they just don't know how to do these tests or have the kind of information that enables them to do well in a test. So one has to be very careful how you measure these things. And to a certain extent, the test results reflects the upbringing or the environment in which a person is nurtured. It's certainly true that being exposed to lots of news and information and having that information at your fingertips does mean that you have access to a lot of information and therefore can potentially know a lot. It doesn't necessarily make a person incredibly intelligent, though, because the two are probably a bit different.
Right.
You can have the Encyclopedia Britannica, which is all the information, or Wikipedia, all the information known to mankind on it, but it's not intelligent. It's just a huge amount of information. How you marshal those facts, how you apply those facts, and how you interpret those facts, that is what we tend to regard as intelligence, and that's a slightly different thing. So I think the two do inform one another. If you're intelligent, you know where to look for information. If you have access to information, you can nurture your abilities. But I don't think that just having a lot of information, going back to my person living in the bush, for example, clearly not stupid, but just not coached in how to be an intelligent person in today's modern world. I think they're two slightly different things. What do you think?
You asking me or Leon? Me?
But both of you, I guess.
Yeah.
No, actually,
Leon, you go first.
No, thanks a lot for the answer. I didn't really think it through. The question just came up while I was thinking about it this morning. So I haven't given it much thought myself. But
thank you very much. I'm excited by what you said, Chris, that I tend to place a lot of value on interpretation of information, because sometimes we can memorize information, we can gather information, but how we apply it and how we use it, I do think that's a reflection of intelligence. But also that an intelligent person perhaps has a better chance of even gathering and storing information than someone whom we don't deem to have a high IQ.
There's an old saying that a person can be a bungalow being a house that's just one story, nothing up top. And so you can have these incredibly bright people in terms of they know huge amounts of information, but they don't necessarily have the razor-sharp mind that enables them to see through a problem and connect dots together, connect unrelated things. And the people who are very good at cryptic crosswords and can see these bizarre kind of abstract connections in things may not necessarily have a huge memory for facts, but they probably would be regarded as more intelligent than a person who has just sat down and learned a lot of information.
All right. Let's go to Peter in Senton. Thank you very much, Leon, for that question. Peter, hi.
Hi, Reddy. Chris, when you spoke earlier on about the plants calculating at night and saving enough energy for the following morning when the sun comes up, the question is now, what if the sun doesn't come up? Like in Johannesburg this morning, we woke up, it's cloudy, there's no sun. So what does the plant do now?
Hi, Peter. Brilliant question. And the researchers, you should go and work for them, because they did exactly that experiment. They jet-lagged plants, and they were able to show that the plant really suffers because it uses its body clock to work out when it anticipates sunrise is going to be. And if you then delay sunrise, the plant uses up its energy at the wrong rate because it thinks the sun is going to rise at a certain time and then it doesn't, and then the plant starves for a while. So this can damage the metabolism of the tissues. It can cause long-lasting damage to the plant. So that's why it's really important that the plants don't get it wrong. And if they do have a bad day like that, then they would certainly suffer. And if you go and read the paper in eLife, you'll see what they did. It's absolutely right.
Thank you very much, Peter. Thanks. We hope the sun does come up. I don't like this kind of weather at all. Billy in Rustenburg, hi.
Hi, Reddy. I've got a question. I bought a small bottle of milk inside, and I wanted to make tea, and it was very cold. And I thought, okay, I didn't have a microwave back then in Rice University. And then I boiled water, hot water, and I placed that bottle inside the hot water. And then, to my surprise, when I opened the bottle of milk, it was ice inside. I was surprised. I never got why that happened.
Hold on, the carton of milk froze when you put it in.
In the hot water.
Chris?
I'm listening to the radio.
Okay.
That's a tricky one. I'm not really sure unless it was frozen already. What usually happens is that because milk is a mixture of two things, milk is an emulsion. In other words, if you were to look with a very powerful microscope at milk, what you would see is a liquid which is made up of a lot of water, that's the aqueous phase, and bobbing around in the water is a lot of little droplets of fat. And they're surrounded by proteins and other chemicals that make the fats dissolve or move inside the water, and that's why you get this emulsion. When you lower the temperature of milk, then one phase can freeze, leaving the other behind. So what you can end up with is the water can freeze, or the fat can go solid inside some of the water, and then you get a very concentrated solution of water around the outside, because not all the water will freeze because it becomes very sugary and salty. It might be that there was some ice in the middle already, and that they couldn't see this because the other liquid was still around the outside. But I don't know why it should happen when you put it in a bath of hot water. That is a little bit counterintuitive. One other possibility is that if the milk is really, really, really cold, and it was just sitting there as a liquid, but really cold, and in the course of disturbing it, you can sometimes bring the milk into contact, or any liquid will do this, into contact with the side of the container and trigger a small ice crystal to form. And this then does what's called nucleate, the formation of a lot more ice in the milk bottle. You can do this with drink bottles, actually. We did an experiment on The Naked Scientist where if you cool down a fizzy drink bottle to about -5 degrees C, then you take the cap off, let the gas out, then the bottle will suddenly start to freeze, and it'll freeze from the top down to the bottom, just from liquid to solid ice in seconds. And it's because you make it energetically favourable for ice crystals to begin to form in the liquid. And once you've got one ice crystal, it makes it much easier for more to form, and then you start forming a complete crystal of ice. And it may be that that's what happened with the milk, that it was quite happy as a liquid, as long as it wasn't disturbed. As soon as it was taken out of the fridge and shaken or disturbed or moved, it then triggered some ice to begin to form, and that then went through the rest of the milk. And because it was ice by then, putting it into the bath of hot water didn't make a huge amount of difference. For the short time it was in there, it's still ice.
Okay, let's go to, is it Tabby? Tabby in Lombardy East. Good morning.
Good morning, good morning. I have a question which has bothered me for a very long time. Now that we're in the middle of winter, and you go to bed and you lie in with your hands outside the blankets, your hands and arms freeze, but your face doesn't freeze. And I'm sitting here at my desk, and my hands are ice cold, but my face, my nose, everything is warm. How come?
I think the simple answer, Tabby, is that about 20% to 25% of the blood being pumped out of your heart at any one instant is going straight up your neck in your carotid arteries and your vertebral arteries into your head. And so with that level of blood flow and blood flux, the level of heat delivery to that part of the body is absolutely huge. And as a result, there's a lot of conduction through from the underlying tissues, and this keeps it much warmer. Your fingers and toes are your peripheries on the end of very long limbs, relatively speaking, with a relatively poor blood flow and a relatively poor surface area to volume ratio. In other words, there's a very big surface of your fingers and very little volume to retain very much heat on the inside. So they lose heat quite quickly, and the body also vasoconstricts them. It closes down the blood vessels supplying those parts of the body to prevent heat loss. So your peripheries are vulnerable for those two reasons. Your head is protected partly because your brain's in there and you don't want to shut the blood supply down to it. And secondly, that there's such a high blood flow up through the tissues to get to the brain that you nourish everything anyway, keep it nice and warm.
Is it Isaac? Isaac calling us from Woodmead. Good morning.
Morning, Rudy. Morning, Chris. My question to Chris, I read somewhere when I was very young that the early sailors believed that they could sail to the east by sailing to the west. I'm talking about the Christopher Columbus, your Vasco da Gamas, the guys who sailed to Africa, in the long time ago. So I just wanted to ask if there's any truth
that they could reach the west by going to the east.
To the east, yeah.
Okay, Chris.
Hi, Isaac. I'm not a historian, and I might get this wrong. So if anyone knows I've got it wrong, please tell me. You can tweet at Naked Scientist, or you can email chris@thenakedscientist.com and put me right. But my understanding is that prior to the people you mentioned, Isaac, people thought that the world was flat. And it's reasonable to assume the world is flat because everywhere you look it seems flat because the planet is so large that the curvature is quite subtle from our small perspective close to the ground. And so people thought the Earth was a giant flat sheet. So if you went sailing off in any direction, then you would presumably just carry on forever, or they even thought that perhaps you would fall off the edge somewhere. And so it was a great surprise to people when these individuals managed to start doing circumnavigations. They could start in one place and go right the way around and come back to where they started. And that's when they realised that the Earth is not a flat sheet at all, but a giant ball. And it's a ball with such a smooth, such a shallow curve that we don't perceive it until you go up a really tall mountain or something, and then you can see that the Earth curves because things disappear over the horizon, and then people began to get this concept of the Earth as a ball rather than a flat sheet.
Tim in Tembisa, good morning.
Good morning, Redi. How are you?
Good.
Hi, Chris.
Yes, Tim, your question, please.
Okay. Why is that when you can't see clearly, maybe if you're reading or you're looking at something, but when you squeeze your eyes, you see much more better?
That's me.
I think that's called age, isn't it?
Thanks, Chris.
Yeah, you're really old, really. The reason for this, Tim, is that there's probably two things going on. One is that when you screw your eyes up really, really small, you're probably doing, most importantly, a squeezing of the lens tissue on the front of your eye. Your cornea, the clear part of the front part of the eye, does about 80% of the focusing of what you're looking at, and the final 20% is the lens sitting behind the cornea, and there are muscles in your iris, the coloured bit, which squeeze or stretch the lens to change how fat or how thin it is, and this affects its focal length, and therefore how clear the pictures are. If you screw up your eyes, you're probably helping to squeeze a little tiny bit on the front of the eye and change its shape very subtly in order to optimize the focus if your lens isn't capable of achieving the right focus itself, either because as you've got older it's got stiffer, or because your eyeball isn't a nice round shape, it's more elongated. That's a condition called astigmatism. Even more subtle could be that if you make your eyes into really, really, really fine slits by screwing up your eyelids really tightly, you can also be doing what's called making a pinhole camera. And this is where if you look through a tiny aperture at something in the distance, then you restrict the amount of light that is coming through that aperture, so individual spots of light from a target that you're looking at come in, go through the hole, almost like a lens, and then fall onto the retina as a discrete spot of light. And this has a sharpening effect, but a dimming effect. So you're not letting very much light into your eye, so things will look much dimmer, but because only a few discrete spots of light will be landing on the retina in the right places for each object, things will look a lot sharper. And that's how a pinhole camera works. And a combination of both of those things could be achieved by screwing up your eyes, I would speculate.
Here's an SMS here. Chris, why, if hydrogen and oxygen are so highly flammable and combustible, when combined to form water, they are not? That's from Philip in Greenside.
Hello, Philip. Very good question. And the reason that hydrogen and oxygen react together so violently is because they have a lot of chemical potential energy. And when they react together, with the hydrogen forming bonds to the oxygen, then they are sharing out electrons, forming a molecule of water, which is a stable configuration with much less potential energy, and therefore you have released the potential it had as the explosion or the energy, and it's now much more stable as water. A good analogy is to think of a hill with a ball at the top, and hydrogen is like a ball at the top of the hill, and oxygen is like a ball at the top of another hill. If you let the balls go, they will roll down the hill until they meet in the middle at the dip between two hills, and there they'll sit. And the energy that they've expended in rolling down the hill is the equivalent to the energy when you reacted the two together. If you wanted them to become excitable again, you'd have to split the balls apart and roll them back to the top of their respective hills, which is what we do when we electrolyse water. We split the molecule apart with electricity and turn it back into hydrogen and oxygen molecules again.
Is it Grant who's in Noordhoek? You are our last caller. Hi.
Hi, Harvard, Chris. I'd like to ask you a question that's fascinated me. We are always told that the universe is receding or expanding, and that is because light from distant galaxies is in the red part of the spectrum. My question is this. My understanding is that the speed of light is constant, regardless of which direction, and it's almost like a cosmological constant, if you understand what I mean. How come light then is blue or red shifted if it's traveling the same regardless of the direction that it's going, and the speed of light is constant?
Hello, Grant. So what Grant is referring to for everybody else is that we are deducing that the universe is getting bigger, because if we look at things far away, we see that the light coming to us appears to be what's called red-shifted. And when we say red-shifted, what that means is space scientists look for certain lines of light which are produced by certain chemical elements. Every chemical element has a unique fingerprint of light that it either absorbs or emits. And if you look at distant objects in the universe, and we know what they're made of, you can see that the line for, say, hydrogen is no longer in the position as it would be on Earth. We see that that line has moved a bit. In fact, it's moved as though the light is more red than it really is. And so we call it red shifting. If things, on the other hand, are coming towards us, we can do these experiments, then you get the opposite effect, blue shifting. Now, the reason that the light does that is because although the light has not changed its speed very much as it's come across space, assuming it's travelling just through the vacuum of space, space itself has changed. So the space that the light is travelling through is getting bigger. And therefore, this has the effect of making the light waves appear to be stretching out a little bit, getting further apart. Not because the light itself has changed, but because the medium it's going through has changed, and this has a stretching effect. So the light appears to be red-shifted. Therefore, we know that the space through which it has travelled has expanded. And this is effectively the light equivalent of the Doppler effect. When you see a police car coming towards you, the sound is a higher pitch than when you see the police car then going away from you. The sound appears to be a lower pitch. And this is because the sound waves that the car is putting out, if it's coming towards you, the sound waves are coming out from the police car at exactly the same rate. The siren is not changing. Mm-hmm. But because the distance between you and the police car is getting smaller, then to your ear, sound wave number 1 arrives, but then sound wave number 2 arrives a bit sooner than it should because the car has driven towards you a little bit in the meantime. This means that you hear 2 sounds arriving sooner than they should, so the frequency is higher.
Okay. Chris, sorry to interrupt you. Will you be available to complete the answer after 10 o'clock? We have to take a break and then the news. Or shall we leave it till next week?
I'd said all I wanted to say.
Oh, okay. Thank you very much, Chris. We'll podcast this. Have a lovely weekend.
Thanks, everyone. Bye-bye.
Bye. Ooh, I lost track of time.